Okay, so the first example I want to do of stoichiometry example problems comes from your review sheet. So unfortunately, the problems in stoichiometry tend to be wordy. Now, I'll tell you that if you have difficulty in word problems, this is the time to practice them because stoichiometry and for the rest of the year, it's all about the word problem. So we need to brush up on our word problem skills. So what I want to do is, rather than putting it on there, I have it in a separate document just so you can see it. So this is the question we're working with right here. Okay, so how many grams of butane, C4H10, must be burned in an excess of oxygen to produce 15 grams of carbon dioxide? Well, it doesn't really matter what problem we're working with. The process is going to be exactly the same. The first thing you're going to do is write down what you're given. So in this problem, I'm given 15 grams of carbon dioxide. So I'm given 15 grams of carbon dioxide. I'm going to set up my conversion. Now I'm going to need to make it kind of long because remember I've got a lot of steps. So my carbon dioxide is here. Well, first step, when in doubt, mole it out. 1 mole on the top of any substance is equal to the weight from the periodic table for that substance. Now, it asked me, so that converts me to moles. Now, it asked me to convert from grams of carbon dioxide to grams of butane because it said how many grams of butane are required to make this many grams of CO2. So I'm going to convert between CO2 and butane, which is C4H10, which is what it told me in the problem it was. So I look at the ratio and I notice that 8 CO2s are in a ratio of 2 C4H10s. Now, some of you are looking at this right now and going, oh, well, that's a 1:4 ratio, Mr. Siegel. And that's true, but I do not recommend reducing it. And the reason I don't recommend reducing it is mental math can cause you issues. The more times you have to think about a problem, the more times you have to work out a number, the more times you're more likely to make mistakes. So just keep it as 2 to 8. This way you don't accidentally go, oh, it's a 1:5 ratio, and you've reduced it down incorrectly, and now all your numbers are off. Just write the numbers that are on the page. Don't make things more complicated for yourself. So that gets me to moles of C4H10, but I don't want moles of C4H10. I was asked for grams of C4H10. That's supposed to be an H, not a 10. That would be weird. Okay, now so I have to go to the periodic table. I have to go to my periodic table, and I have to calculate C4H10. So I know that for carbons is 4 times 12.01 plus 10 hydrogens, parentheses. Remember what I always say, parentheses are your friend. And remember, round to 2 places past the decimal when you're adding, when you're looking up numbers from the periodic table. So it's 58.14. Now, remember what I said, parentheses. I'm going to parentheses around everything on the top, a parentheses around everything on the bottom when I plug it into the calculator. So again, I whip out my handy dandy calculator and I go to town on my calculations. I'm going to slide this over to the side so I can see what I'm actually doing. So I'm going to open my parentheses and I'm going to type 15 times 2. I'm going to skip the 1 because that's just obvious. And I'm going to do second answer. And that's my 58.14, but the reason I'm using answer is because it takes 4 times for me to click for 58.14, but only once to do answer. Close the parentheses, divided by, open my parentheses back up again, 44.01 times 8, and hit enter. And the answer is 4.95 grams, remember units, of butane. So just slightly less than 5 grams of butane will produce 15 grams of carbon dioxide. Very efficient reaction. Let's look at another example. Okay, so this is example number 3 from that same review sheet. Okay, so now I'm doing this one here. So it says, over the years, the thermite reaction has been used for welding railroads in incendiary bombs for welding railroad rails in incendiary bombs to ignite solid fuel rocket motors. The reaction is blah, blah, blah. What masses of iron 3 oxide and aluminum must be used to produce 15 grams of iron? What is the maximum mass of aluminum oxide that could be produced? Yes, I know there's a typo. Okay, so there's actually 3 things that I need to calculate. My given is 15 grams of iron. But they said what masses of iron 3 oxide, which is Fe2O3, and aluminum, which is Al, must be used. That's two separate calculations right there. Then there's a second question, and then the second question is, what is the mass of aluminum oxide? So basically, what they're asking me is, using this same given of 15 grams of iron, they want me to perform 3 stoichiometry calculations. So when I do this, I have to make sure I plan out my calculation. So my given is not going to change in any one of the problems. Now I'm just going to write them all out at once to save myself some time. Most problems won't do this. Most problems will ask you for 1, maybe 2 things, but this one's a fun one because it allows us to practice our stoichiometry problems. So, first step, when in doubt, moles. Mole it out. Now again, the first step in all of them are going to be the same, because I'm using the same given. Now, you ask, why do I use the same given? Simple. I know that given's correct, 15 grams. They put it in the problem. If I were to, let's say, do the stoichiometry for the iron 3 oxide, and then use that number that I just got, I don't know if that number's right. I'm assuming that number's right, but I don't know that number's right. So I can't make those kinds of assumptions, and so it's better to use the number that the textbook or the problem gives rather than numbers that I may have screwed up as I was doing my calculations. So now, I go to my chemical reaction, and I notice that there are 2 Fe's. Now I'm just going to go in order through the problem because it asked me for all of them. To 1 Fe2O3. That's right. Remember, folks, there's a 1 there, even though it's not written. To 2 Als, and to 1 Al2O3. So now it asks me to calculate the mass. Now remember that mass means grams, not moles. So I know that 1 mole goes on the bottom. And then the weight from the periodic table goes on the top for each of them. Now I'm writing in the units because I'm going to have to do some calculations. Now this one's easy. I know aluminum is 26.98, but I'm going to have to calculate the other ones. I'm good. I'm not that good. Okay, so let's do the iron. 2 times 55.85 plus 3 times 16 is 159.7. Now since I've already got that number on the screen, I'm just going to perform the calculation for that whole stoichiometry right now. So again, open your parentheses, type in your given, 15 times 1 times 1 times, oops, here we go, and that 159.7 divided by, open your parentheses again, 55.85 times 2 on the bottom, and I get 21.4. And of course I always circle my answers so I know where they are. Oops. Okay, now I do the second one. Open the parentheses. 15 times 2 times 26.98. Now notice there's an extra number in this one because in the first problem, 1 was the coefficient for the iron 3 oxide, but now 2 is the coefficient for the aluminum. So I have to make sure I put that in there. Divided by 55.85 times 2. Hey, shocking, it's the exact same bottom. Okay, this is 7.25 of aluminum. And then the last one, I'm going to have to do 2 calculations again. I've got to find the weight of the aluminum oxide to start. So 2 times 26.98 plus, now I know oxygen is 3 oxygens is 48, so I'm just going to plug 48 in. 101.96. Whip that calculator back out, and go 15 times second answer. I'm telling you, that second answer key is going to save you minutes on tests and homework. Divided by 55.85 times 2. Close it. It's 13.69 grams of Al2O3. And that's it. Those are the three answers for that problem. Again, notice, none of them are hard. They're a little tedious, yeah, but once you get good at them, they're a piece of cake.